The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker is Yuan Cheng. He is from the National Taiwan University of Science and Technology. His co-authors are Remy Lescain and Leonardo Swibo. Deformation capacity and strength of RC flexural members constructed with high-strength materials. I'll turn it over to Yuan.
Today, the presentation topic is deformation capacity and the strength of RC flexural members constructed with high-strength material. And this work is contributed significantly by one of my PhD students, Leo, to the right, and two of my colleagues, Professor LeQuinn and Professor Lepage from the University of Kansas. These two colleagues give me tons of hard time. I changed a lot of the presentation material in the past few months, including the presentation title. So, but anyway, thanks for their input. Their input improved the quality of this presentation as well as my knowledge about this topic. So, this is the overview of today's presentation. I will start with a brief introduction, and then I will discuss a design issue for the use of high-strength concrete, and then after that, a couple recent study of RC flexural member using high-strength steel will be reported, and some experimental result will be discussed, and finally a preliminary conclusion will be given. But before I start my presentation and probably gonna lose some of my audience, I would like to share with you some of my thoughts about Professor White. And this picture is taken probably 2 years ago. And if you look carefully, there is an invisible gap between me and Professor White. So this is how intimidating he is to me. And probably due to his fame, and I just feel he is intimidating. I was so scared to talk to him or asking questions during my years in University of Michigan. And my thesis advisor is my bridge to connect me and Professor White. But 6 years after I graduated, even right now, I think his intimidating level decreased, but still there, 50%, I guess. That's 50%. So this is the first thing this is my fear about him. And the second thing is Professor White is fully support his student, and he took best care of us, and even after we graduate, and that's something that I learned from him a lot. And the last thing, and probably the most important thing that I learned from him is his integrity, and his attitude toward the academic and both academic and administrative work has great influence on me. And I really hope that I can transfer this value to my student, which is also shown other people except me and Professor White. So I really hope I can transfer his value to the next generation. Okay, so I will start the introduction. The two pie chart lists here are the construction material for the world's top 100 tallest building, and according to the CTBUH data. And on your left is the data collected up to year 2000, and on your right is the data collected up to the 2013. So in the legend, the steel refers to the steel structure, concrete refers to the RC structure, composite refers to the steel and the concrete acting compositely in the main structural element. And the mix refers to the steel, distinct steel and the concrete material above or below each other. So if you think from the figure, in the past decade, the RC concrete high-rise building rises more than double, and the steel structure decreased to only 40%. And think about this. Before 1970, the steel structure used to occupy more than 90% of the world's 100 tallest buildings. So I think from this pie chart is a good news to all of us. We should feel excited about this because we have more work to do. As the demand of high-rise building increases, so does the material strength. And there are some concerns about the use of ACI, about the application of ACI building code in the high-strength material that I will talk about later. This is the code limit for seismic application. And FC-Prom, basically, they set up a lower bound of 3 KSI, but they set up an upper bound for the flexural reinforcement steel. So starting with high-strength concrete, the definition of the high-strength concrete is varied from one area to another. And if you look at the figure listed here, as the concrete strength increases, the strength corresponding to the peak increases, as well as the descending slope. So one question regarding the flexural design is, what is the upper bound concrete strength that the current ACI code specified equivalent stress block is still valid? And most of the previous researchers answered these questions through the strength point of view. The curvature associated with the nominal moment strength has been overlooked. And it should be reminded that the curvature associated with nominal moment strength has nothing to do. It was originally developed for the flexural strength and was not intended to evaluate the member deformation. And the current code uses that primarily for 2 purposes. First, it calculating the phi factor for flexure, and then determine the need of spatial boundary element in structural wall. So if the code continue to use this design criteria, the curvature has to be determined. So to illustrate the curvature issue, we have collected 12 stress block models. The first 6 listed here are recommended either from the official documents such as ACI ITG4 or the building code such as ACI building code, Euro code, and the Japanese code. Some code has a clear limit for the concrete strength, for example, Euro code and the Japanese code, but some code do not, including the ACI building code. Another 6 model listed here are the stress block model proposed by the researchers. And the astorial sign next to the FC prime here indicate that the upper limit of the concrete strength is determined by the authors because they do not provide it, and we just determine based on their database, data bank. So for beam cross-section and the reinforcement layout shown on the upper right position, this is the analytical result of the flexural strength. And the vertical axis represents the nominal moment capacity determined from each stress block model divided by the nominal moment capacity determined according to the ACI code. As indicated by several previous researchers, the flexural strength of an RC member without actual load is insensitive to the stress block models. However, this is the analytical result of the curvature. As you can see from these 2 figures, the difference can be as much as 60% from one stress model to another stress model. So we believe that there is something that we can work on to determine which one stress model that gives us the most closely the definition that current ACI code has. And it has to be resolved, as I say, because the ACI code uses that for 2 very important reasons. And then I would like to move to high-strength steel. Compared to the high-strength concrete, research work on high-strength steel is relatively limited. In Japan, a 5-year national project from 1988 to 1993 is launched to develop design guideline of high-rise building using high-strength steel. And from that study, they conclude that to have a good good performance, the high-strength steel is necessary to have one, distinct yield plateau. The second, Fu to Fy ratio greater than 1. That means you need to have a strength hardening behavior. And the third, the elongation of the steel as large as possible. Just give you an example. The most common type high-strength flexural reinforcement used in Japan right now has a distinct yield plateau with a minima strength at onset of strength hardening, not less than 1.4%. And the Fu-Fy ratio has to be larger than 1.25. And the elongation is greater than 10%. That is SD685 high-strength steel. In United States, I think Fu to Fy ratio greater than 1.25 is probably the only requirement for the flexural reinforcement. And this ratio is actually based primarily on Professor White and Professor Sosen's work back to 40 years ago. It's quite amazing that 40 years ago they already found this. And the figure at the right provides the explanation. So this is a cantilever beam. You have a load at the tip. So this is the critical section where moment is the largest. So when the tension steel starts to yield, which is refers as a state 1 to the figure below. Once the steel yield, if the existence of the yield plateau increase the curvature rapidly from state 1 to state 2. However, this rapid increase does not contribute to any member deformation. To increase the member deformation capacity, a curvature area is needed, and that can be achieved only when you have a steel that exhibit strength hardening behavior. So, in the 1976 ACI 350 report, a ratio of the Fu-Fy ratio greater than 1.25 is proposed. And that ratio is later adopted in 1983 ACI building code and has remained unchanged until right now. Later, McDermott in 1998, through an analytical study of an imaginary rigid frame system, he found that the Fu over Fy ratio greater than 1.25 is a prudent choice. And also, he further suggests that we need to specify a minimum elongation strength for the flexural reinforcement at least 10%. So, experimental result of the two previous studies collect here to evaluate the some design recommendation I just addressed before. So the first study consists of 3 specimens. The first specimen is specimen SP1 reinforced with conventional grade 60 longitudinal rebar. Specimen SP2 and specimen SP3 reinforced with grade 100 high-strength steel longitudinal rebar, which in compliance with SD685 Japanese standard and the ASTM 1035 standard. And the A over D ratio, I will show you later. And for the second groups, in the second group, there are 2 specimens. The first specimen is named as CC4X. It is reinforced with grade 60 longitudinal reinforcement. For the specimen UC4X, it is reinforced with grade 97 high-strength steel from Germany. And all specimens are in each group were designed to have equivalent flexure capacity. Also, the transverse reinforcement is provided to exceed the demand from probable moment. And this is the experimental setup used in the 2 studies. In the first study, the specimen was tested in the upright position, and the load is applied at the top. For the second group specimen, the specimen is tested horizontally, and the load is applied back and forth through the column stop. And the material test result is listed here. for each group of specimen, basically the concrete strength is controlled very close to each other so that we can rule out the influence of the concrete strength. And the steel tensile test result is listed here. So for SD685, there is a distinct yield plateau here. And for the high strength A1035 steel, it shows a so-called roundhouse stress strain properties. And for the German grade 97 bar, it has a distinct change of slope after yielding. And this is the average test result of 3 steel coupon. As you can see from this table, the A1035 is the only rebar that shows the elongation strength less than 10%. And for most of the grade 60 bar, the FU to FY ratio is generally around 1.5, which is much higher than the SD685 and the N35 and the grade 97. Those high strength steel considered in this study, they all generally have a FU to FY ratio around 1.2. And this is the historic responses between moments and the cold rotation of the first group specimen. Specimen SP1 failed due to severe buckling of the longitudinal rebar. Specimen SP2 failed due to fracture of one corner bar and the buckling of the rest. Specimen SP3 failed due to fracture of all 3 reinforcement. The spacing of transverse, you can see that the spacing of transverse reinforcement seems a little bit wide. So the spacing of a transverse reinforcement in specimen SP1 is around 6 dB. The dB refers to the rebar diameter, and but that is around 8 dB in specimen SP2 and SP3. Despite this wide spacing of transverse reinforcement, the specimen SP2 and SP3 reinforced with high strength steel achieve 4% ultimate drift capacity. And that drift capacity here is kind of different than the first specimen, because the first specimen defined the ultimate drift capacity in specimen SP1 is defined as the load dropped from the peak, dropped 20% from the peak, while SP2 and SP3 is the drift capacity where the test terminated. I terminated the test primarily due to the safety concern because the rebar already fractured, so I cannot continue to push it. And this is the historic response of the second group specimen. Both specimens did not fail under reverse cyclic loading up to 5% drift. And they subsequently subject to monotonic push, and they fail due to the fracture of longitudinal rebar with drift capacity more than 15%. 15%. So based on the limited test result, we may conclude that the beams reinforced with grade 60 and the high strength longitudinal reinforcement exhibit comparable deformation capacity. If buckling, shear failure, and the bond slip can be prevented, a minimum drift capacity of 5% can be achieved, provided that the steel has at least 10% minimum elongation. And previous research also indicate that the higher FU to FY ratio leads to a better spread of plasticity, and then benefit the deformation capacity. So we start to examine how far the plasticity extends in each of the specimen. So this is the readings of strain gauges at a distance approximately d away from the support face. Apparently, specimen SP1 longitudinal reinforcement in specimen SP1 and SP2 yield up to the 3% drift. And then they also indicate one important thing that was found 40 years ago. The yield plateau here, the existing yield plateau contributed to no or negligible deformation. So I just repeat the work of Professor White again. And So, but for the high strength steel A1035 in specimen SP3, the yield strength is around 0.67. It seems that this level, the specimen SP3 did not reach the yield strength at the same distance. However, it should be reminded that strain gauge reading is very sensitive to the crack location. So from the analysis of exterior deformation, we found that the curvature of specimen, curvature distribution between specimen SP2 and SP3 are very similar. So we may conclude that all specimen has sprayed the plasticity up to a d distance away from the column face. Similar thing that can be observed in the second group specimen. So the second group, the strain gauge at the d distance away from the column stop yield up to 3% drift. So it seems that all of the specimen we tested in this study spray the plasticity up to the distance d from the column face, regardless of the FU to FY ratio. So the authors are suspicious. Actually, the authors were suspicious that whether the FU in the steel can be reached under reverse cyclic loading, because it seems like buckling generally govern the behavior. So we were suspicious if FU can really be reached. And also, the spread of plasticity, the influence of spread of plasticity on the deformation capacity is not clear from this research, because it seems like most of the specimen reinforced with high strength steel have comparable deformation capacity as the control specimen. So it's not clear that if spread of plasticity has anything to do with the deformation capacity. And the stiffness is also a study in this presentation. So basically, we constructed a bilinear model for each historic loop, and we found that the linear K1 portion is proportional to the tensile reinforcement ratio. This is the first group specimen. This is the second group specimen, and the post-yield stiffness seems to proportional to the second modulus of the steel. The second modulus is defined as the slope between the yield point and the ultimate point on the steel stress strain curve. And this is the strength evaluated using the ACI code, specify equivalent stress block and the bilinear, which is a perfectly elastic perfect plastic bilinear steel properties. And it seems that the experimental result over the predicted result is for all test specimens is within 25%. So that indicates that the current code equivalent stress block and the assumption of perfectly elastic perfect plastic steel property for high strength steel is appropriate for the strength evaluation. However, this I want to broaden out for in specimen SP3 that uses ASTM 1035 high strength steel. It is labeled as grade 100, but the test FYE and to the specified FY is 1.2, more than 1.2. And this nominal moment capacity, predict nominal moment capacity is based on test material, so it does not include this value here. So we think that the code to better estimate the overstrength factor, it's better to have a limitation of the test Fy to the specified Fy. So with that, I would like to conclude my presentation. The equivalent stress block recommended by the codes or proposed by the researchers results in a similar nominal flexure strength but significant different curvature associated with it. The limit test results suggest that being reinforced with grade 60 and high strength flexural reinforcement considered in this study exhibit comparable deformation capacity. If buckling, shear, and the bond slip can be prevented, a minimum 5% drift ratio can be achieved, provided that the high-strength steel has at least 10% elongation. The spread of plasticity for all specimens extends to a distance d, distance away from the column face, regardless of the Fu to Fy ratio. The fracture strength of a member using high-strength steel considered in this study can be reasonably predicted using the equivalent concrete stress block and the elastic perfect plastic steel properties. Thank you for your attention.